Oh, wow. Okay, so let me just check if this works. Oh, what happens now? The clicker doesn't seem to be working after we go into presentation. Yeah, the clicker. Yeah, it was working right now. Maybe I should. So as soon as we hit share it. Oh, hello. How are you?
What's wrong?
The clicker was working prior to this, and I know it worked in the previous one. As the arrows are working. Yeah, now it's working. What's going happen? Oh, okay. Ah, perfect. No, it's fine. Thank you for your help. Okay, good afternoon, everyone. I think we might as well get going. I'm sure people will come along as soon as they finish getting some tea, they'll probably come across. So thank you for attending the tutorial. This tutorial is based on a book, which we should have had out in April, but we are a little bit behind time with it. So it's going to be out in October this year. And I'm not sure if anybody's read our first book, which was Hyperheuristics Theory and Applications. Okay, so that was published in 2018. This is now the sequel to that book, and this is specifically on now looking at where the field is advanced to since then. So a quick outline of the tutorial. I'm possibly not going to get through all the content that I've put on this outline because we only have just under 2 hours. So some of it, you may have to wait for the book to come out and the next tutorial, but I'm going to try and cover as much as I can. So if you work in the field of hyperheuristics, you'll know there's been a vast amount of advancement since its early inception. Since the first search in the heuristic space rather than the solution space directly, there's been a lot of work. And what we've looked at are different areas where it has advanced in both in terms of how hyperheuristics have progressed, but other advancements in AI helping to advance hyperheuristics, but also at the same time, how hyperheuristics have actually been used to advance things. So firstly, just an introduction. How many people are familiar with hyperheuristics? Okay, that's good, because the first overview is on what hyperheuristics are, just very, very briefly. That itself was a different tutorial, which I used to give previously, but that itself could take another 1.5 hours, but I'll just give you a snippet of what hyperheuristics are. One of the new directions in hyperheuristics is assessing their performance. You'll see traditionally the performance was assessed based on optimality, but the whole aim behind a hyperheuristic is generality. So we're going to look at how we can combine that. And with that, we've introduced different levels of generality. We're then looking at how hyperheuristics can be used in automated design. So if you work at AutoML, or if you're also looking at the automated design of search techniques themselves, what difference has hyperheuristics made to that area? We all know there's been a lot of work with optimization for machine learning, but currently there's a big boom around the whole idea of machine learning and optimization. And hyperheuristics is no exception. This is another area where machine learning is making a difference. A lot of the work that came up with hyperheuristics was focused specifically on combinatorial optimization, discrete optimization, and there hasn't been a lot of work done on continuous optimization since in the first, you can say in the first era of hyperheuristics. But subsequently, there has now been work on continuous optimization, and where are we and where can we get to from here with continuous optimization? What's also emerged is while hyperheuristics can be used to design other techniques, what can we do to actually design hyperheuristics? Because the decisions are not always easy to make when it comes to designing a hyperheuristic. So I'm going to speak a little bit about the automated design of hyperheuristics. And then transfer learning in hyperheuristics, how transfer learning can be used in hyperheuristics. I mean, we know transfer learning from neural networks. There's been a lot of work on evolutionary transfer learning. So previously at Gecco, I used to give a tutorial on transfer learning in the evolutionary space. So there's also work done with transfer learning in hyperheuristics. And then lastly, the whole idea of explainable AI and how we can actually incorporate explainable AI into hyperheuristics. And why do we need explainable AI in hyperheuristics? Okay, and then finally, like with most tutorials, I'd just like to leave it open for any discussion that may emanate. Okay, so just quickly an overview of what hyperheuristics are and why do we even want to look at them. So traditionally, when we apply any search technique, what space do we actually work in when we apply a search technique? So suppose you're solving the traveling salesman problem, or you're solving some type of routing problem. What if we're searching, if we're using a genetic algorithm or we're using any meta heuristic, what search space are we typically working in? Exactly, we're working in the solution space. So for example, if you're looking at a routing problem, you'd randomly create routes and then you'll do some optimization to try and see which is the best. So, but it's not perfect working in that solution space, right? There's problems. You can get stuck in local optima. There's also, in some problem domains, you may not be able to reach some parts of that solution space. And this is where the whole idea, which I'm quite excited about, is working in alternate spaces. The first such space is hyperheuristics, but since then we've also been looking at multi-space search, where you look at more than one space and you work in more than one space. And why would it be an advantage to work in more than one space? You can possibly solve some of the problems that you have with working in the solution space by indirectly searching that solution space via another space. So when hyperheuristics first came up, that wasn't the aim. No one actually thought that you could actually solve problems that you had with the solution space by working in the heuristic space. The main idea behind hyperheuristics was to raise the level of generality, which I'll speak a little bit about just now. So, but subsequent to that, we found you can actually do fantastic things with working in your heuristic space and mapping it across to a solution space. There's actually a lot of power in that. Okay, so when hyperheuristics came up, I'm not sure if anybody's come across, if you work in the meta-heuristic field, the whole idea of up-the-wall research. Okay, so the whole idea of up-the-wall research is we're trying to find the next best meta-heuristic that can beat the previous meta-heuristic in solving the problem. Now, what usually happens in that context? Usually we end up with a situation where you've got a technique that will work very well for some problem instances, but will not work as well for other problem instances. So that's the first level of generality that hyperheuristics was initially developed to achieve, was to actually try and find an approach that will produce good results for an entire problem set or even beyond problem sets. You'll see I'm going to speak a little bit about cross-domain hyperheuristics just now. But in addition to that, can you actually find a technique that will just give you good results across different data sets without giving you extremes, either very good results or very, very poor results? So that's the first level of generality. The second level of generality, so if we go back to our traveling salesman problem, if you had to implement a GA for the traveling salesman problem, could you take that same GA as is and apply it to solving, say, a nurse rostering problem? No, you'll have to redo operators, you'll have to redo different aspects of it. So that's the second level of generality that hyperheuristics try to achieve, where you speak about the domain barrier. The domain barrier actually provides a separation now between your domain-specific things, like the heuristics that you're going to search for in the heuristic space, things for evaluating them to see how good they are, and the actual approach. So if you're implementing a hyperheuristic, approach will not ever have to change, irrespective of the problem domain that you're applying to. What will change is what you're searching for in the space, which are the low-level heuristics, which I'm going to speak about. I'm calling them low-level to distinguish them from all the other heuristics, given how overloaded the term is. So if I speak about low-level heuristics, we're speaking about heuristics that we're actually searching for in the heuristic space. So main difference between hyperheuristics and what you've been doing all the time is we're using exactly the same meta-heuristics, but just the space we're searching in is different. And so whereas if you were doing your traveling salesman problem or your vehicle routing problem, if you were searching in the solution space, elements of the population will be the actual routes. If you're searching in the heuristic space, you're searching for the heuristic that can either create a route or improve an existing route. That's the main difference with working. You could use exactly the same meta heuristics that you used previously when you explored the solution space. So when we space and what we're looking for in the heuristic space, there's two types of heuristics. So either you're getting heuristics to create a solution, or you're getting heuristics to improve an existing solution. So those are the two types of heuristics that you can actually get. And those heuristics that are used, if you're doing some search to look at heuristics to create a solution, we call those construction heuristics or constructive heuristics. If you're looking at heuristics to improve an existing solution, and that solution may be created by randomly creating it, or using a construction heuristic to create it, or a selection constructive hyperheuristic, which we're going to speak about a little bit more just now, then that whole idea is you're perturbing some things to move from one part of the search space to the other. You're perturbing some point that was created somewhere else. And what does your hyperheuristic do? It chooses the move operators or the perturbation heuristics that will actually move you through the search space. That's essentially what it does. Okay, so please at any point, it's going to be a bit hard to see if there are any questions online because I don't have anybody helping with that. But if anybody has any questions, I will try and monitor the online questions as well. But also, if you have questions from the floor, please stop me at any point, either if you want to add anything. That will help. Thank you very much. As long as you can see clearly from where you're sitting. Thank you. Yeah, they should just pop up on the top there. It should just say, thank you. Okay, so please stop me at any point if anything's not clear, or if you have something to add, if you've had some experience on whatever I'm speaking about that you'd like to share as well. Okay, so selection constructive hyperheuristics, this is where it's all started. So to give you a very, very simple example, suppose you want to create a timetable. And in your search space, you want to create an initial point, and your GA is going to, maybe you want to create a timetable for scheduling exams, for example. So what would basically happen is you could randomly create that initial point. Alternatively, you could use construction heuristics to create it. So typical construction heuristics, which come from graph theory, are things like allocate the exam that has the most students that would be possibly involved in clashes first. Allocate the exam that will require the biggest venue. So you want to allocate exams so you can end up with a feasible timetable. So those that are more difficult to allocate is what you'd allocate first. And that's essentially what a construction heuristic does. So construction heuristic will work out which are the things that should get priority to be put into a solution to help you get a better solution quicker. If you were doing things like routing, what would a typical construction heuristic be when creating a route? You want to add cities in, you want to minimize your route or the distance or some cost of the route, you'd use nearest neighbor. That would be a typical construction heuristic. So essentially what selection hyperheuristics do is they actually will choose the right construction heuristic for you to use at each point when creating an initial solution. So essentially it's when you're creating that initial point in the search space. If you were doing a multi-point search, then of course the construction heuristic will be used to create your entire population. So instead of randomly creating and this was my first encounter with construction heuristics. I went on sabbatical and almost went through a depression. I could not get any good results. I was using a straightforward GA for a timetabling problem. And a very, very simple thing. I just stopped creating my population randomly. I used a construction heuristic to create the elements of the population. And I got almost close to the best known results. And then I could then do improvements on that. So just having an informed point in the search space to start from, or an informed set of points, if you're looking at multi-point search, actually makes a big difference. So your construction heuristics automate this process for you. Selection perturbative will do the same thing, but instead of selecting perturbative heuristics, it's actually selecting, instead of selecting construction heuristics, it's going to select perturbative heuristics. So if you look at your routing problem, you've got an initial point that was a route that you created either randomly or using something like nearest neighbor. You then want to move to other parts of the search space that actually get you closer to your optimum that you want to go to. So you want to perturb something in that route. And so what a selection perturbative hyperheuristic does, it allows you to choose an operator to make that perturbation. So if you look at some of those operators that you could choose, or some of those low-level perturbative heuristics that you could choose, it could be, for example, swapping two cities in that route, or taking out a segment and replacing it, or swapping two segments in that route. So that's essentially what your selection perturbative. Now we get to the exciting hyperheuristics. I always love working in GP, so I've always been very excited about generation heuristics. So if you look at all these heuristics that we're selecting, where do they come from? Any suggestions? So you remember your selection constructive hyperheuristic will choose which constructive heuristic to use to create an initial solution, and that's at each point of the solution. Your selection perturbative will choose which perturbative heuristic to use. Where do those heuristics come from? Anyone? We created them, right? So some researchers sat and came up with these heuristics to create initial points for timetables, initial points for routes. But what generation hyperheuristics allow you to do, they allow you to automate that process. Now we know whatever heuristic you use and whichever technique you use it with, there's always a no free lunch on that. So probably different heuristics will work well with different approaches, but the challenge is, can we manually go and create all those heuristics? It's just too time consuming. So generation hyperheuristics take that away from us. They actually automate that process. So they will come up with a new construction heuristic for you, and they will come up with a new perturbative heuristic for you. So of course, the generation construction will come up with construction heuristics, and generation perturbative will come up with perturbative heuristics. So that's an overview of hyperheuristics. I just want to stop there at that point to see if there are any questions or if there's anything that's not clear. I'm just going to quickly summarize. So essentially what is happening when you work with hyperheuristics as opposed to working with what we traditionally do in optimization and working in a solution space, we're actually mapping our heuristic space onto a solution space. So what we are looking for are heuristics that we can optimize, a sequence of them to create a new solution, or a sequence of heuristics to improve an existing solution, or basically coming up with new heuristics. Now, how does this mapping happen, and what causes the happening? And you've got your two spaces. You've got your heuristic space where you've got your heuristics in. You've got your solution space where you've got your solutions in. How do you map between them? So basically, whenever you take a sequence of heuristics in your heuristic space that you're searching for the heuristics, or the single heuristic that you're searching for, or the new one that you've come up with, you have actually got to use that to go and create a solution and then evaluate the solution, and that value maps back. So it's a very simple mapping. Of course, you can only map in one way. So from a sequence, you can produce a solution, but a solution may produce more than one sequence, and you can't actually get back or more than one heuristic. So that's essentially how the mapping happens between the spaces. Of course, because of that, this can be computationally expensive, given the technique that you are using to drive search in the heuristic space, because you've got to evaluate each thing in the heuristic space by using it to solve the problem. And that's, of course, one of the challenges with hyperheuristics. But things like high-performance computing have helped us overcome that. Okay, any further questions?
So I think what I'm struggling to see
Yeah.
in the heuristic space, it doesn't feel as granular, because I think lots
Yeah.
of heuristics I have would be like take sort of graph.
Yeah.
But I don't see how that would be as granular as
Yeah, so that's probably true. So you basically have, you're going to have a single heuristic, or you're going to have a sequence of heuristics, and they're going to map over, but that may have some advantages yeah. Yeah.
That's not like came from a bucket of
No. It's true, Jen. So to give you an example of what generation is, I'll give you an example of how selection would change from generation. So let's take perturbative, because most people are familiar with perturbative, right? So for example, if you were looking again at a routing problem, because I think everyone can relate to routing problems, you basically have a route, and perturbative heuristics that you'd select from, probably the box of perturbative heuristics, would be things like remove a city, add a new city, swap cities, delete a sequence, swap sequences. But now, what would your generation space look like? Your generation space will actually be made up of commands that will create that perturbative operator. So we've actually done some work where we've broken down what actions do, if you take any domain, what are the typical things that you do when you perturb? You may swap, you may add, you may delete, but those could be the big commands, but they will actually be combined with components of that solution for a particular solution space. So you're creating a brand new one. That's a very subtle difference, and for a long time in the field, people were confusing both, because sometimes you can use something like genetic programming, but you may still be doing selection. You may be selecting the existing ones. For example, if you use genetic programming to create a rule that tells you which heuristic to use, that's still selection, although you're using genetic programming. But if you're coming up with a brand new heuristic, and that's where I said it's an advantage from having to manually do it, because there's only so many heuristics that we can think of. Whereas if you use something like genetic programming or grammatical evolution, sorry, is everybody happy with genetic programming, grammatical evolution? I'm just speaking about it, assuming everyone knows what it is. But the main difference between genetic programming and genetic algorithms is, again, genetic algorithms search a solution space, whereas genetic programming searches a program space. So it'll come up with either an equation for you or an algorithm for you, etc. Yeah, so that's the main difference. But it's exactly what you're saying. When we generate, that's the exciting one, where you're constructing new things. And one of the things that have come up, sometimes you come up with heuristics that humans can't think of, but actually are doing quite well. And when you actually look at them, you can actually see what it's doing. Because GP is white box, you can actually see exactly what the heuristic is doing. Yeah, any other questions before I go on?
Perhaps just so perhaps it's coming.
No, but it's fine.
When you best hyperheuristics, so when you generate
Yeah.
this process, apply on the same problem.
That's a very good question. So you need training and testing the way you would typically do with any machine learning problem. There's two things you can do with them. You can create a disposable one, but that's very expensive. So you could create a disposable one just for that problem instance. But you could also create one for more than one problem instance, because then it can be reusable. So we do typically the same thing that you would do with any other machine learning technique, where your fitness, it will then be training and validation, and then you'll have a test set after that you will run it on. But that was a very good question. And any other questions before we go on? Okay, so this is just an overview of hyperheuristics. I'm just going to quickly go into each of those a little bit, just to give you an idea before we start going into the advances in hyperheuristics. Okay, so the other typical thing that happened at the inception of hyperheuristics, they were used essentially for combinatorial optimization problems. So you'll see a lot of the work, and my first tutorial that I gave on this on hyperheuristics theory, based on our book on hyperheuristics theory and application, looked a lot at combinatorial optimization problems, because when they came out, they were used to actually to find solutions and generalizable solutions for combinatorial optimizations that can typically be scaled up for industry. So your routing problems, your scheduling problems, those type of problems is what they were focused on. But just a quick overview of each one of them. So the whole idea is we have some construction heuristic. These heuristics have come up somewhere. Some human expert has come up with these heuristics, and they typically used to create an initial point before you apply your optimization technique. But what we are now saying is, can a hyperheuristic, instead of using, usually what would happen is you use one heuristic, it will create a solution, and then you will search from that point. Or if it's a multi-point search, you'll create multiple solutions, initial population using that heuristic. But what is different if you use a selection construction hyperheuristic? It will select a different heuristic for each point of creating that solution. Each time you're assigning something to build that solution, it will use a different heuristic, and it will work out which are the right ones to use and which are the best ones to use. So that's the main difference. So it usually outperforms selection constructive hyperheuristics, usually outperform manually created heuristics, because you are now using a different one at each point. We don't have anything online as yet. Okay, thank you. Okay, so the whole idea behind selection construction hyperheuristic, like I've mentioned, is to create an initial solution. And the advantage it has over the way it's manually done is it actually facilitates choosing more than one heuristic when you're actually solving a problem. Traditionally, the type of searches that have been used are local searches, things like simulated annealing, variable neighborhood search, taboo search. We've done a lot of work in our group with genetic algorithms, where each chromosome then is a sequence of heuristics that you optimize, and then you actually apply it in order to create a solution. And a lot of the work, and that is why you see I'm going to use both these examples a lot, although we've moved away from these examples, but a lot of the early work were done on these two domains, examination timetabling and one-dimensional bin packing. But you'll see we've actually moved far away from that now. We use hyperheuristics in our real-world examples. But what is good is to always to include them, because then you can go back and compare all the new things. Can you compare to the initial hyperheuristics that came out? So those were one of the two main areas. One-dimensional bin packing problem is where you're trying to pack items into bins to minimize the number of bins. And the standard construction heuristics were human-derived. I mean, there's a lot of work done in construction heuristics for bin packing. So things like first fit, best fit, where you have the least amount of space wasted in the bin when you put something into the bin. Those were all the construction heuristics, and the hyperheuristic then chooses which ones to use in order for each different item to be put in a bin. Okay, any questions before I go on? So selection perturbative hyperheuristics, you could possibly use exactly the same local search techniques and multi-point search techniques. But when this was introduced, this was the first hyperheuristic that was introduced, and a lot of work went to this. And for this type of hyperheuristic in particular, there's a very simple technique called a single point search that is defined in the context of specifically selection perturbative hyperheuristics that have a heuristic selector component and have a move acceptance component. So perturbative heuristics, everybody's happy with that. These are what you typically call move operators in search. So where you're actually doing something to a point in the search to move it to the next point. And what the hyperheuristic essentially does, the hyperheuristic decides which one of these to apply. So you normally have some initial solution or some initial point in the search space, and then you just apply these consistently until you get to a point where you have no improvement. So you'll take the sequence, you'll apply the entire sequence of perturbative operators that come up, and then you usually continue until there's no improvement. Okay, so the whole idea behind a selection perturbative hyperheuristic is it will select perturbative heuristics, not hyperheuristics. And one special kind which has a lot of power, and you wouldn't think it would have that much power, we've actually found with the work that we've done, and you're going to see in some of the examples that I speak about, especially when you've got computationally expensive problems to solve, is your very simple single point, what the community calls a single point search selection perturbative hyperheuristic. It has two components, which is your heuristic selector and your move acceptor. And you can basically use anything there. You can take anything out of searches and use it in there. The simplest one is where you randomly choose a heuristic, and only if it results in an improvement, then you accept it. And Ahmed Kiri, who's around but is not here now, he used this very simple hyperheuristic for the school timetabling competition, and it was actually placed in the first three, or I think it was the third. Just that simple idea, just by working in a different space, actually allowed for you to get around to other points in the solution space for that the school timetabling problem, which is the most complicated of all the timetabling problems. It's the most constrained problem. But just so we always use this very basic baseline. But for that heuristic selector and move acceptors, you can basically use anything. You could take things from other existing local searches, like you could use the concept of a two-bool list for heuristic selector. You could use something like the acceptance criteria from simulated annealing for the move acceptance. So there's different things that you can play with for that. So these are just some examples of heuristic selectors which have been quite effective. Choice function is used a lot and different variations of the choice function. And I'll speak a little bit about, we've used this a lot in the work that we do. What a choice function does, it's a form of reinforcement learning where it looks at how well heuristics have performed over time from the beginning of running your hyperheuristic to the point that you're at. And based on how they perform, they get a score. And then based on the score, they get select or not. But it also takes time into consideration as well. And it also takes coupling of heuristics. How do they work in pairs? It takes that into consideration as well. So reinforcement learning, random has also been used in move acceptance. Usually these are move acceptance criteria that have been used in other searches that are pulled out and actually used. So like simulated annealing, great deluge, improving only, etc. And then, of course, there's multi-point searches. I mean, the challenge with multi-point searches are just the computational cost. So you can search the heuristic space in the same way that you would search a solution space, but using multi-point searches instead. So each chromosome basically represents a sequence of heuristics, whether they're perturbative or whether they're constructive, that you are actually going to apply in order, either to improve a solution or to create an initial solution. Okay, and again, these are the main two problems that have been used. I think there's also been some initial work with personnel rostering. So when the field first came up, there's been a lot of work done in those two areas. Okay, any questions and comments before I go on to generation hyperheuristics? Just a quick overview of them. And I take it there's nothing from the online attendees as well. Thank you. Okay, so generation, as we spoke about just now, the whole idea behind generation is it's quite time consuming to manually come up with heuristics on your own. So it takes a number of different experts trying a number of different things. Can we automate this process? And that's the whole idea behind generation constructive hyperheuristics. So with generation construction hyperheuristics, one of the main contributions to this field is genetic programming. So genetic programming and variations of genetic programming have been used largely for both construction hyperheuristics and for perturbative hyperheuristics. So the whole idea is we want to create new hyperheuristics, and we want to create the new hyperheuristics by using some information about the domain, some domain-specific knowledge. So if you're looking at construction hyperheuristics, essentially you want to get something that directs you on which component to put in next when you're building a solution. So usually what makes up these construction hyperheuristics, you could either have a construction rule or an arithmetic function. So if you were looking at an arithmetic function that gives it a priority value, then you'll have arithmetic operators combined with problem attributes, or even the human-derived heuristics. If you're using a rule, you could also have a conditional statement involved in there. Okay, so the approaches used have chiefly been genetic programming. Grammar-based GP has also been very popular. Grammatical evolution has also been very popular for this as well. What grammar-based GP does in grammatical evolution, using a grammar to specify or restrict your search space, so you can ensure that the heuristics you get are feasible heuristics. They actually make sense. But in doing that, you also reduce the size of your search space because you block off the parts that would not be feasible, for example. And again, these are just some of the early examples. You can see a lot of work was done in both those areas. So generation perturbative, here generation perturbative, it took a lot longer to actually come through. Okay, so I'm just going to switch to that. So the generation perturbative hyperheuristics, you're basically doing the same thing as you did for your generation constructive hyperheuristics. The only difference is you now, the example I just gave to the person that just asked a question just now was, we would then have different elements in our function and terminal states. You'll still have genetic programming being used or grammatical evolution as the main drivers. But what you actually put in the set will be things that will make up a perturbative hyperheuristic. So there hasn't been a lot of work done. There's two main studies that I'm aware of that come up with new perturbative heuristics from scratch. A lot of the earlier work just combined existing move acceptance components and moving heuristic selectors. But there's two studies. One is by Napier Edinburgh, a PhD student from there, Christopher Stone, and the second was a master's student at our university, where they've actually broken up. They've looked at perturbative. So the work we've done actually looks at perturbative heuristics and actually looks at, okay, if you do any perturbation, irrespective of your problem domain, what are the things that you actually do? You either swap things, or you move things, or you move sequences, or you will take something out and you reallocate it. So it's your ruin and create heuristics. Those are all the standard things that we'll do when you do perturbations. But how do they differ? They differ based on what you apply them to. So basically, based on those main actions, you then have that being your main function set for your GP, and the terminal set will be made up of the problem-dependent solution components. So if you were doing a routing problem, the problem-dependent solution components are cities in the route or parts of the route. If you were doing a timetable, would be the periods, the rooms, the exams, portions of the timetable. And then basically you come up with new heuristics by combining those. And optimization then drives that. So we're going to look at assessing hyperheuristic performance. For those people that have worked in hyperheuristics, you'll know that essentially when the field came through, we'd assess your hyperheuristic in the same way that we'd assess your metaheuristic that was working in the solution space. Now, do you think that's good or do you think that's bad? Any suggestions, any comments on that? Okay, so one of the things we looked at is, are we doing the right thing in the way that we're assessing hyperheuristics? So this is one of the earlier papers that we worked on. So essentially what people did is they did the same thing that you would do with up-the-wall research. They would look at a problem and say, okay, based on optimality, this hyperheuristic is performing well or not performing well. But that to some extent defeats the purpose of achieving generality. Because sometimes when you're achieving optimality, you're not going to achieve generality. And we need to somehow find a balance of both in order to examine the performance of a hyperheuristic. So if you look at hyperheuristics, what are their main aim? The hyperheuristics' main aim is to perform well over a set of problem instances. But at the same time, if you have something that generalizes well, but has very bad optimality, would you want to use it? No, right? You want a good balance between both of them. So our first step was to look at an alternative to just using optimality. And that was the idea of bringing in generality. So the whole idea was, in addition to just using optimality, we also look at bringing in generality. Some of the earlier work, and especially the work with cross-domain hyperheuristics, the way they looked at the way a particular or compared to hyperheuristics as performing better in terms of a set of problems, is if you had 10 problem instances, they would assign each of the hyperheuristics a rank based on whether it got the best or second best or the third best value for each of the problem instances, and then they would sum the rank. But the challenge with that, what's the challenge with that? You are now taking all the problems into consideration, but you're still basing it totally on optimality. You're still not looking at generality in any way. So the whole idea now is to look at this over a set of problem instances, and how do we do that? So what we've done is we've introduced a measure which looks at the standard deviation of differences from the best known result. Now that best known result can be the best known in the literature, but if it's a first study that you're doing, in that particular study, you may have a best known result, right? That you've actually got in that study. So that's what it does. So it looks at an alternative to just optimality. Okay, so, and now I'm going to have to move to the computer because the people online are not going to see me when I point with the pointer. Okay, so basically what it does is, this is your standard deviation formula. That's just your standard mean formula. But what's important is the differences that it's taking. So what it does, your O subscript I is the value that the hyperheuristic has for that problem instance I, and the BI is the best known value. So just to make it a little bit normal, it just takes the difference of the absolute value over the average of the differences. And then of course it's basically giving you a percentage. Sorry, that should be a BI, not a VI there. It's giving you a percentage, so it's normalizing it. And of course, that's only going to make sense if you don't have both those values being 0. And if both the values are 0, it will just be 0. So basically, a smaller value is a better generality. And what it's actually assessing is a generality over the problem set of problem instances instead of just looking at optimality. So for a hyperheuristic, you will get a generality score. Oh, and I've left my clicker behind. You'll get a generality score rather than a value for each problem instance. Okay, I'm just going to stop at that point to see if there are any questions before I go on.
Sorry, but this assumes it's normally distributed.
Yes, yeah.
That's the assumption that all the
Yeah, so basically it's basing it on the assumption that we and the reason that we've done it is from our previous work we've seen that we do generally have a normal distribution for it. So that is why it was taken. But that's exactly correct. Okay, any other questions? Comments at this point? Okay, so just to give you a very simple example, if those were our two hyperheuristics, and those are the values that they're trying to achieve, and we're trying to minimize, and we know those are the best known values that we've got. If we then go and work out our SDD for each one of them, so H1 is 9.2. I'm not going to do the math. You can fiddle around with later to see if I didn't make any mistakes or not. And the next one is for SDD for H2 is 7.94. And you can actually see if you look at the optimal values that you cannot, there's no correlation in terms of a positive correlation between generality and optimality. You can actually have something that performs very well optimally may not achieve generality. And that often is the case. So those are the two SDD values. So if we look at this case, the hyperheuristic H2 will achieve better generality than H1 based on the SDD value that was used. But so this is just the generality measure. But if you look at this, do we want to look at generality only? And that's the biggest question, because you could get a hyperheuristic. If you look at this example, that could work very well in terms of generality, but is it any good if it's not achieving optimality as well? So the whole idea, and this is where the multi-objective optimization comes in. So the whole idea is, can we find a way of getting a solution that attains generality and optimality? And I've done very simple multi-objective optimization, but this is an area which we're looking at building on. And I'm just going to give you some simple ideas which we published on this, but there's still a lot more work to be done in this area by using multi-objective optimization. So there's two ways in which we can do this, and this is the traditional way it's been done. And actually, this is the wrong way that we have been doing it, and it has to be fixed. Because when we're optimizing, we're still optimizing only for optimality, but post the hyperheuristic being applied and getting a solution, then we're evaluating for both optimality and generality. So this is traditionally what's been done. We basically drive whatever search you're doing in the heuristic space using optimality by mapping over to the solution space. And the solutions produced by the hyperheuristic are then after that assessed on both in terms of optimality and generality. What is the disadvantage of that? I mean, it's very clear that the main disadvantage is when you're doing the optimization, you're only assessing for one objective, but you're then evaluating on both objectives. So this is traditionally the way it's been done. I mean, even in earlier work, we wouldn't even evaluate over all the problem instances that the hyperheuristic is worked on. If there are different data sets, we'd actually do them differently. And so in that way, we're not actually assessing generality and optimality at the same time. So the way that we need to do it is actually during the optimization. And there's more than one way of doing that. Depending on what technique we're doing to explore the heuristic space, we could actually build that into whatever the assessment measure is, the performance measures in, and we make sure that both generality and optimality are used. In addition to that, we also possibly need to use a multi-objective optimization algorithm to do this. And then comes to the question, we're no longer dealing with one problem instance that we're working the optimality for, because usually what happens traditionally with hyperheuristics, we'd work out, we'd run the hyperheuristic for each problem instance, and then we'd get what its values are, the objective values that it's obtained. But now we've got to actually assess over the set of problem instances. And again, now the idea is we possibly take a machine learning approach, where we have a training and testing set and a training and validation set when we're assessing the performance of the hyperheuristic. Okay, so I'm just going to stop at that point before I go on any further. Okay. So these are some very, very simple examples. And the way we've actually looked at optimality is by then taking rank, using rank as the optimality measure, because we want to actually assess optimality over the problem set rather than looking at optimality per problem instance. Now, this is just one way of doing this. This area is also an area that needs further development on. So if anybody wants to research doing this better, like we said, one of the conditions is that we know from previous experience, we've generally had a normal distribution for the hyperheuristics, but that may not be the case. So there needs to be future work in looking at an alternative for that. In addition to this, we've just used ranks here because this is what was traditionally done, but there's still more exciting work that can be done here on how to assess optimality across a set of problem instances. So essentially here, one of the ways that this was traditionally done for the HyFlex competition was if you look at H1 and we look at just 5 problem instances, we then rank your hyperheuristics. So we've got 3 hyperheuristics there, H1, H2, and H3, and we're essentially assigning a rank for each one of them based on how they perform. And you could either sum those ranks or you could take an average of the ranks, right? And in that way, you're getting an optimality measure. So in that way, we can look at optimality across the problem instances. Any questions before I go on? Okay, now if we look at our SDD values and we look at our average rank and we want to actually now take both into consideration when we're assessing the performance of these 3 hyperheuristics, we could do a very simple weighted sum scalarization. We know the disadvantages associated with that, right? We could pull in any direction. But if you wanted to do that, in some cases that may actually work. So what I've actually got here, and I'm just going to quickly go back because I've got to use my pointer again, is if we look at it, we've got the SDD value, and we've done a very simple min-max normalization. Okay, so that would be our weighting of the different objectives. And we said, okay, well, we'll get the hyperheuristic, the generality will be 60, the optimality will be 40, and then we do a simple min-max normalization so that we get, when we actually weight them, they actually are together. And so that's our generality, that's our optimality, and that's basically the NSD, the STD, this column is the STD normalized, that's the average rank normalized. Okay, and then if we take the weighted sum, we basically say our hyperheuristics. Now, what do you think? What do you think that weighted sum does? Is it a good reflection or a poor reflection? Okay, so if you look at H1, it was better when it came to optimality, generality, but it was actually worse when it came to optimality. And then its overall value is 0.652. If we look at H2, it was better when it came to optimality, but worse when it came to generality. And then we've got the same for H3. It was better when it came to optimality than H1 than with generality. So if you compare them 2 by 2, it doesn't make sense. So if we look at H2 versus H1, H1 actually has the worst value. And I think that does actually make sense if you are giving generality of a better value, right? We're weighting generality higher. So it does work. And if you look at it the other way around, if you look at H2 and H3, you've got basically that H3 has better optimality. Let's just quickly check. No, sorry, H2 has better optimality, and it also has better generality, and overall it's getting the better value. Okay, so that's one way we could do it. Any questions or comments before we go on? Oh, that I just used it as an example. So it depends on what the user wants. So you could play with that ratio. This was just an example just to show you how it would work. Yes, then you're prioritizing optimality. But you can also already see the problems we're doing it with the scalar vectorization.
This problem is not convex, right?
Yeah.
So do you have the scalarized, like Cheryshev scalarized?
So this is just one option you could use, but it's not the best option for exactly the same reason that you said. So ideally, the best is to use some type of Pareto function, but the best would actually to use a multi-objective optimization algorithm to possibly to work with it in the domain when you actually in the such way. You could use another scalarizing function as well. Yeah. That would probably be the easier than using something like a Pareto. So the question, I'm not sure if everybody heard it online, is that that is a particular type of scalarization that may not work in all domains, right? So you could, the suggestion, which is a very good suggestion, is you could use another scalarization problem. Our alternative was to, instead of using a linear scalarization, because I don't particularly enjoy that, I don't feel it's powerful enough in a lot of situations, is to maybe use something like a Pareto comparison and come up with the Pareto function, and then ultimately using a multi-objective optimization. But you are right, you could use some very simple other scalarization functions that will work quite well. Yeah. Long time. Yeah. Yeah, so these are problems for the multi-objective people to look at, and we are more than happy to collaborate. I think we are speaking about a collaboration on exactly that. So is to collaborate on the best type of techniques that we can take from the multi-objective community and use for this. So again, a similar idea could be if you're looking at Pareto optimality, but it's almost a simple Pareto function rather than using a multi-objective optimization function, where if both objectives, you have your hyperheuristic best for both objectives, then you're fine. You don't have any problems. But if you look at that, if you're comparing H1 to H2 or H2 to H3, there's none of them that you have it best for both objectives. Okay, so it's usually straightforward if you have it best for both objectives. And then you need to see which you're giving priority to. If you're giving priority to one, then you can see which one's better than the other. If you're giving a priority to optimality or a priority to generality, it depends. But if you're not giving priority to either, a very, very simple thing that you could do is you could find the difference. You could normalize, find the difference between where one's worse than the other, and then go with the one with the less difference. But these are just very simple functions that you could use. The idea is to eventually look at how much of multi-objective optimization do you need, and how full-blown do you need to make that multi-objective optimization. Okay, any questions or comments? So when it comes to assessing selection constructive hyperheuristics, do selection construction hyperheuristics have to be comparable to state of the art? Any suggestions? Would you think, what is your selection constructive hyperheuristic doing? It's at the end point of a search. It's actually giving you an initial point in the search space. So instead of randomly creating an initial point or randomly creating your initial population, your selection constructive hyperheuristic is actually either giving you a set of initial points or an initial point. It will be really good, and actually that has happened, that the results have been compared to state of the art, but that's not what we're actually trying to achieve. We still want to do optimization beyond that. Okay, so the whole idea is it achieves the same as a construction heuristic. It's basically finding initial points that can be optimized further. And essentially, you want to compare the performance to human-derived heuristics to see whether it's giving you an improvement over it. And generally, that's what it does do. It does give you an improvement over human-derived heuristics, but it's choosing the right heuristic to use at each point instead of just using one heuristic. And then, of course, you also want to compare to other selection constructive hyperheuristics that exist. That's the whole idea behind it. So yes, we have had cases where they do give good results, and in some cases are comparative to state of the art, but that's not the ultimate goal when you're trying to assess your selection constructive hyperheuristic. So if you look at selection perturbative hyperheuristics, now those are different. So what do you think they should do? What is your selection perturbative hyperheuristic doing? There you are moving, you are perturbing in the search space with some initial point that you've created either randomly or by using a selection constructive hyperheuristic. So in that case, yes, it should be able to compare with state of the art. So it usually has an initial solution that's created either randomly or using a constructive hyperheuristic, or a selection constructive hyperheuristic or constructive heuristic. And you could compare to other selection perturbative hyperheuristics. It can be compared to a state of the art approaches as well, because that is actually doing your search in the search space from an initial point. And you could include with state-of-the-art approaches. Okay, any questions or comments about this? Anything anybody that's working in the hyperheuristic field wants to add or discuss? Okay. Then if you look at generation constructive hyperheuristics, again, very similar to selection construction hyperheuristics. And here we've had some very good results. I think there was work done on packing problems where, although these were just generation constructive hyperheuristics, they actually beat state-of-the-art approaches. It's just because of the heuristic that was formed, did really, really well. So the whole idea is we want to create a heuristic to produce an initial point, and usually your performance is assessed by using the heuristic to create a solution. And again, these should be compared to human-derived heuristics, and they should be compared to other, both generation and selection hyperheuristics. So this just gives an idea. So generally what was happening, everything was compared for optimality and everything was compared to state of the art, which actually doesn't make sense in the context that you're using it. So for example, you wouldn't take a construction heuristic and compare it to state of the art. You'll do more optimization before you can do that. Here's the generation perturbative hyperheuristics. Here we are creating new move operators. So essentially they should be used with some search technique because the move operators on their own cannot achieve it. And we know by the no free lunch theorem, different perturbative operators will work well with different search techniques. So essentially we should compare it to other perturbative operators by iteratively applying them and using a very simple search to actually compare them. Or we can actually use it with a full-blown search algorithm and compare it. Okay, so that's an overview of assessment of hyperheuristics. Any questions or comments on that? We're actually coming to that. So linked to this is the levels of generality. Because what we've done is we just dumped everything into one box. If you had a hyperheuristic that has to produce a good result for a problem instance and one that has to work across different problem instances, we've been treating them the same way. But you'll see that's generality level 4. But the whole idea is instead of just using the ranking, when you're actually applying your heuristic to the heuristic space for the chess challenge, in addition to the ranking, you also use the generality formula, the SDD, and you actually find some way, either by using some scalarization function, by using some Pareto function, or by using a multi-objective optimization in some way. So then when you're searching the space, you're searching for a part of the space that has both generality and optimality. But I'm going to speak about the different levels of generality. In particular for selection, because the chess challenge was for selection perturbative hyperheuristics, so that should be comparative to state of the art. Any other questions? Okay, so that brings us to your question, generality level. So when hyperheuristics came out, whether you were trying to find a hyperheuristic for a set of problem instances, or you were trying to look at cross-domain hyperheuristics, basically the same assessment was used. The only difference with the cross-domain is we did a ranking like you've seen. But this now made us think a little bit about what do you want to achieve with your hyperheuristic and what are the different levels of generality that you may want to achieve with the hyperheuristic. And this depends on how well you want to perform over which data instances. So the simplest level is what we all played with initially when hyperheuristics came out. We had some discrete optimization problem and we wanted to solve it using the hyperheuristic. And that's level 1. So we are looking at 4 different levels. I'm hoping there'll be a 5th one now that we've done work in continuous optimization and combining or getting a hyperheuristic that could work well over continuous and discrete optimization. So if you look at a level 1 problem, you have a single problem, you have a single benchmark set. So you may have something like the Christopher's benchmark set for capacitated vehicle routing, or the Skoll benchmark data set. I'm using again discrete optimization. If you're looking at continuous optimization, you have benchmark sets, different benchmark sets for function approximation, for example. So you want that hyperheuristic to work well over that problem set. The second idea is you may have a single problem, but you may have multiple data sets. So if you look at the capacitated vehicle routing, I think you have the Christopher's, you have the gold, and you have a number of different sets of problems. But the main thing here is you could have 10 different problem sets, but if they all have the same characteristics of the problem, it doesn't make any difference. So basically, we're speaking about problem sets that have different characteristics for the problem. So you're looking at different types of problems, but you're basically solving the same problem. Now, where we've done things wrong here, usually when we apply the hyperheuristic and we evaluate it, we'll evaluate it for each of those problem sets separately. You don't want to do that. You actually want to evaluate over the problem sets. And you could even do a testing the way you would normally do with machine learning techniques. So that's where we have a single problem, but we have a number of benchmark sets. The third level is where you have a single domain. So if you look at bin packing is a domain, but you can have 1-dimensional, 2-dimensional, and 3-dimensional bin packing problems. If you look at examination timetabling, you have, well, I should rather say educational timetabling, because then you have examination timetabling, you have school timetabling, and you also have university course timetabling, and then you have curriculum-based, and you have pre-enrollment or post-enrollment based. Sorry, curriculum is pre-enrollment, and post-enrollment based is when you create the timetable after everyone's enrolled. So there you have a single domain, but a number of problems in that domain. And you may want your hyperheuristic to work well over all those problems in that domain rather than for a single problem domain. And there you've got multiple problems, and they should come from all the different types of problems within that domain when you're assessing your hyperheuristic performance. The last one was the one that you mentioned. This was where we had a major breakthrough with hyperheuristics, where you can get a hyperheuristic to produce good results over different problems. And I think we had 6 different problems. It was personnel scheduling, traveling salesman, capacitated vehicle routing, packing, max sat problem, and I've forgotten what the other one was. I think there were 2 types of traveling. It was traveling salesman and capacitated vehicle routing, and also one-dimensional bin packing. But the whole idea here was you create a hyperheuristic that can work well over all those problems. So when you assess the performance of the hyperheuristic, it should be across all those problems. The way it was done was that the hyperheuristic was ranked, and then the rankings were summed. But as I just showed you just now, we've then left out generality. We haven't worked out the generality. So with that, you would also include the SDD, and you somehow assess for the SDD value and the optimality value. So I'm hoping now that hyperheuristics have also been working in continuous optimization. We can now have a fifth level of generality, where we're actually looking at type, and type being discrete versus continuous, for example. Can you get a hyperheuristic? The other thing about these levels of generality, that chess competition with the cross-domain was specifically for selection perturbative hyperheuristics. There's still a lot of work to be done for all your generation hyperheuristics and also your selection construction hyperheuristics. So if anybody's interested in that, that's open as well to work in those areas. So I'm just going to stop at this point and see if there are any questions regarding any of the things I've spoken about so far. These 2 concepts are linked. Like I said, I'm not an expert in multi-objective optimization, so we're looking to collaborate on this with people that are working in multi-objective optimization. This is just my little snapshot of multi-objective optimization, but we clearly need multi-objective optimization when we're assessing it's definitely at least bar objective. It can even get bigger than that if you want to bring other things into consideration depending on the domain. So a lot of the real world problems, sometimes you need efficiency brought in as well, or green computing brought in as well. So this is a bigger problem. And then linked to assessing for more than one objective and assessing your hyperheuristics for more than one objective is the whole idea of these different levels of generality. Because you need to know the level of generality that you want to attain. And we haven't done that. We've always been evaluating hyperheuristics for a set of problem instances, and each problem instance individually, irrespective of the generality level that we are trying to attain. Okay. Yes. Yeah. Yeah, so that's just, so if you're looking at, you have hidden benchmarks, it's still level 4 because you're still assessing in the same way. It's just the competitors don't see it. So you as the person organizing the competition, when you assess, you'll assess for both those values. But then you could have, you still have 2 objectives. You still have generality and optimality, but it should work. It's just adding on another n data sets. Okay. Any other questions? Okay, so this is just to give you some examples. If you were looking at level 1 hyperheuristics and you were looking at hyperheuristics applied to a single problem like examination or bin packing, generality is achieved with a particular benchmark. So we're looking at it's going back to your question now, but now we're looking at it specifically for that problem instances. Both generality must be over the problem instances, and we're looking at optimality over the problem of instances. So these are examples. So if you were looking, for example, examination timetabling, you'll use a different examination timetabling benchmark sets. If you're looking at it for bin packing, you'll use a different bin packing. And so again, optimality is also for both generality and optimality will have to be achieved over all the data sets. Okay, then if you're looking at level 2, where level 2, you have a hyperheuristic that's applied to multiple benchmark sets for a single problem. So optimality must be across all those benchmark sets. Generality must also be across those benchmark sets. So for example, if you were looking at examination timetabling, here instead of treating each of those sets individually, they're all going to be one whole pool of problem instances that you're solving. And like I said, you could also do training and testing if you wanted to do with that. Similarly with the bin packing, where previously they were treated for level 1 as separate sets, we're now sitting over all of them. Okay, and then if we look at level 3, it's basically the same idea that you're looking at for level 2. It's just you have different problems, and for the different problems, you have the different problem sets. So again, we've got educational timetabling, school timetabling, course timetabling, examination timetabling. if you looked at bin packing, you could have 1D, 2D, and 3D. So both generality and optimality must be across the data sets. And again, you could do training and testing. And then we come to our highest level of generality, which we have thus far, which is the whole idea of working across problem domains. And the idea here was, now there's all 6 listed. The one I forgot was flow shop scheduling. So here is where you want your hyperheuristic. And this competition was specifically for selection perturbative hyperheuristics. You actually want them to work across those problems. And rather than having a hyperheuristic will work well for some problems and not well for other problems. And again, you want generality and optimality across these problems. Okay, and therefore we have some aggregated form of performance measure. Let me go back to. So what would happen as a competitor, you will work on just these problems, but your solution should be able to generalize on the hidden problems. So all that will happen is it's exactly the same way it was run without generality before. Before it was only run and ranked with optimality. So what would happen now is when you as a competitor take part, you'll work out your generality and optimality on this, but when the organizers run it, they will add the extra data sets and then just work out across that. No, I haven't come across that. Yeah, that's a good idea. Yeah. Okay, thank you. Okay, any other questions or comments? Okay, so now we're going to come to, as I mentioned at the beginning of the tutorial, we've just gone past the first 2 chapters of the book, so, which has 12 chapters. So I think there's a lot of work that I've got on the slides that we're possibly not going to cover, but I'm just going to start looking at the next area. Okay, so this is an area that I'm also very passionate about. So like I said, our first book was on hyperheuristics theory and application. Our second book was on automated design. So a lot of the work that we've been doing is actually looking at hyperheuristics for automated design and hyperheuristics, how hyperheuristics can be used in automated design. So the first thing I'm going to do is just give you an overview of what I mean by automated design, and then we can go through and start looking at how hyperheuristics have been used. So I mentioned earlier that the very, very simple hyperheuristic, the one that is just a simple single point search hyperheuristic that combines something like a simple choice function together with some type of improvement only accepting one can be quite powerful. And I'll give you some examples where we've got some good work done with that. So when you're designing anything, whether it's a multi-objective optimization algorithm, whether it's a local search algorithm, whether it's an evolutionary algorithm, what are the different things that you've got to think about? Finding your solution, and when you're designing that algorithm, what do you have to do? So for example, if you're doing a genetic algorithm, you'll have to think about which operators you're going to use. Linked to finding your solution is what the fitness function is that you're going to decide. What are the parameters that you're going to use? If you were designing a neural network, how many layers, what layers form your neural network, what are your different parameters? So these are basically design decisions that we make. I mean, to start off with, we've even got to decide which algorithm we're going to use, right? So, and these are things that could take long and they could take trial and error. And for this reason, there's been a lot of work into automating this process. And so the first thing straight up is which algorithm should I use? Can I automate that process using some type of optimization to decide which algorithm it is that I'm going to use? And then secondly, this has been where a lot of the work has been done. This is where AutoML's first focus was, the whole idea of configuration. So if you had to look at a genetic algorithm, what mutation rate are you going to use? What crossover rate are you going to use? What's your tournament size going to be? What's your population size going to be? What's the length of your chromosomes? And we know those things aren't easy things to find. So there's a lot of work has been done into automating this. Neural networks, the whole area of neural evolution, then more recently led to neural architecture search. Okay, so coming up with the actual architecture of your neural network. So that's another set of decisions to be automated. Algorithm composition. So how can you use existing algorithms, break them up into their building blocks and use them to create new algorithms? How can you compose algorithms? So there's this work being done. So my colleague who's doing this book with me, that's the area that she works in, is algorithm composition and using machine learning to come up with new algorithms. Wrong. So the last one, which is my favorite, which is because I love GP and I've done a lot of work in this, is to come up with something brand new all the time. So the idea of coming up with new construction heuristics, new move operators, new genetic operators, with neural networks, you come up with new loss functions, new activation functions. We've even done work with GP where you could come up with a whole neural architecture. And so these are the things that we do. And why would we want to automate this? There's two main reasons. The first reason is we know this is a time-consuming process, and it's hard for us to get it perfect. It's by trial and error that we play with these things. If we automate this could be running in the background somewhere while we're sleeping or while we're off on holiday, and then we can actually see we can get the architectures we need, we can get the optimization we need. So that's the one reason. It's laborious, it's time-consuming. The second reason is sometimes the optimization can come up with things that we don't think of. It can come up with architectures that we don't think of. It can come up with certain parameter configurations that we don't think of. And that's the reason to look at automating this. Now, there's a number of techniques that are involved in automation. Reinforcement learning is one of the main techniques that I use. So you actually doing this on the fly while your algorithm's running, and reinforcement learning is picking up what's happening and is configuring for you. There's work done with genetic algorithms. But again, heuristics have proven to be very, very effective for some of these decisions. And that's some of the things that I'm going to look at. So I'm taking some case studies from what we've done in our group and how we've actually used them to do different types of automated design. Okay, any questions or comments before I go on? Please try and make it interactive. I'm going to get a bit bored of hearing my voice only quite soon. So I take it online. There's still nothing as yet. Okay. No, it's fine. Maybe I'll start asking some questions to make it more interactive just now. Okay, so we have two types of hyperheuristic, selection and generation. I'm not going to into generation. We know what it can do. So all those new things that it comes up with, the new operators, the new loss function, the new activation function, that's usually GP, and often GP and generation hyperheuristics become synonymous. But where the power lies in hyperheuristics for automated design is in using selection hyperheuristics. It's because it can achieve quite a lot that other optimization techniques can achieve, but it actually takes a shorter time depending on the type of hyperheuristic that you're using. So the first approach, so if you're looking at a selection hyperheuristic, what is the selection hyperheuristic doing? So it's either selecting a set of algorithms to use, and in that way you're hybridizing your different optimization techniques, or it's actually selecting parameters for a particular algorithm. So that may be things like your learning rate, number of neurons, number of layers, etc. Alternatively, it could be selecting different algorithms that it wants to put together, or for your GA, it could select the different values. So the first approach that we tried is actually making the components that you're selecting, making those the low-level heuristics. Okay, but that can also be challenges if you bring challenges if you have continuous domains. But the one thing we found that makes your search space even bigger. So that you're now no longer moving or working in a solution space, we're working in a design space. So that actually makes your design space bigger. So the second approach that we looked at is you create whatever your design is, you randomly create it. So if you want to hybridize meta-heuristics, you randomly create that string of hybridized meta-heuristics, and you can have different meta-heuristics with different parameters. If you want your different parameters for your GA, your population size, your tournament size, you randomly create that initial design. So you randomly create the initial design, and the hyperheuristic then works indirectly on it. It actually searches a heuristic space that will choose perturbative operators that will change the design, and that we found to be the most effective one. So we've used it for algorithm hybridization, and we've used it for algorithm configuration, and you'll see just now we've used it a lot for different types of neural network design. So instead of searching the design space directly, the way you would search a solution space directly, you're now searching the heuristic space, and you're actually mapping it over to the design space. So if you look at typical perturbative operators that will apply to this design, I mean, for some of our problems, they actually are design specific depending on what you're trying to design, but they're basically the same idea of what you do in perturbation. So either you change, increment a particular parameter value, or you decrement a particular parameter value, you change values, you swap values, etc. So the standard things that we tend to do. Okay, so I'm going to now go through some case studies. And I just want to give people some time to chat. It looks like I'm not going to get through most of the book. I'm just getting through the first 3 chapters of the book. But what I'll do is just give you a brief overview of the other chapters and what I was going to speak about. But I think we'll probably just get through the whole automated design section, and then I will then just give you an overview of it. So one of the case studies that we used a selection perturbative hyperheuristic for was for multimodal learning. So the whole idea behind multimodal learning is we typically do unimodal learning. And this is a machine learning, so it's multimodal machine learning. So what we generally do is if you want to, for example, diagnose whether somebody has COVID or not, you would take their chest x-rays, you'll maybe take some data that has pneumonia x-rays in it, you'll compare both of them and you'll say, okay, that's my control set of images that people have COVID, people don't have COVID, and that's just images. Okay, so that's unimodal. Alternatively, COVID, you may have patient stats. You may have information about the patient in terms of blood pressure, all of that, right? And then that's using quantitative data. So with multimodal, so there you'd have different classifiers that will use just the quantitative data. Multimodal is using more than one type of data. So if you wanted to use multimodal learning for COVID diagnosis, we'll have classifiers that will work with the quantitative data and will work with the image data. Now, what is the big question if you're working with both sets of data? What comes to your mind straight away? If you have two sets of data and you want to use machine learning for both, and at the end of the day, you just want one outcome, does the person have COVID or not? Any suggestions? What would you've got now two different classifiers, two sets of data, how you combine them, right? How do you select the different classifiers? What's the best classifier for the quantitative data? What's the best classifier for the image data? You may even have audio, so you may even have a third data set. And you then want to find out which are the best ones for each of the data and how you combine them. So generally this was done manually. And so people manually would actually play with the different models for each type of data. And then we'll try and work out, okay, which is the best model to use for each type of data. But then you also have a set of combiner techniques, which is the best way in which to combine the output from the different data. So, and that is essentially how multimodal learning works. So combiners normally will combine the output, whether you're doing regression or whether you're doing classification, it will combine it. So what this work did, it's a student in my group that worked on this. The whole idea was to look at automating that process, automating the process of actually multimodal machine learning. And this was essentially done by using a selection perturbative hyperheuristic, and GA actually drove this. And the two things that it had to do, if you were doing a classification problem, it had to work out which was the right classifier for the different problems, but it also had to work out which is the right combiner. And similarly, if you were doing a regression problem, it would have to work out which is the right regressor for each of the types of data you have, but also which is the right way to combine them. Any questions or comments before I go on? Is there anything anybody wants me to just go through again? So this is the whole idea now of using optimization and machine learning, and the optimization is essentially a hyperheuristic. Okay, so essentially your multimodal classifiers and regressors that you want to find those that will provide the right combination of them and the right regressors and want to produce the best results. So we use a genetic algorithm. Essentially, what your chromosome was made up of is each type of model for each type of data. But remember, they could all have different parameters. So you could have 6 VGG16s or 6 LSTMs, but they could have different parameters in them. And in addition to that, the different combiners that can be used. And in all cases, and the work has changed since then, since we did the study, is all the models were pre-trained, but of course that causes some types of restrictions because you actually want to train them while they're being optimized. So we used some pre-trained models, and then initial population generation, we just randomly created the chromosomes. Selection tournament selection was used to choose elements of the population, and then just straightforward genetic operators that you would do to a linear string. So your standard crossover where you do 1-point crossover, and the mutation where you randomly change part of the string. Okay, so combiners, these are the different combiners that were included in the chromosome. So it was K nearest neighbor and multi-layer perceptron, and of course different versions of them with different parameters. For classification, those are the different models included, and each of the models, the reason you see 12, 12, and 12 is they have different parameters linked to them. And then that's for the image data and for the quantitative data. So where did we get all these models from? It's basically what is typically used for this type of problem, the type of neural networks that have been used for this problem, those that perform the best, those that performed somewhere in the middle, and different parameters for them. And then similarly for the regression problems, we had image, we used those VGGs, 2 VGGs and ResNet, and then for regression, For the quantitative data, it was mainly multi-layer perceptron, support vector machines, and random forests, again, based on what worked well for those particular type of problems generally. And these were used for specific problems to now try and see how well they worked. So if you look at the applications, because the biggest challenge was getting multimodal data. For COVID, that was fine because you could get chest x-rays and you could get quantitative data. Our biggest challenge was now trying to acquire multimodal data. And a lot of the time we had to create some of the data sets. So movie content was easy to get because movie content, the student had a bursary from a broadcasting company. So we could actually get movie content. We could get both images and we could get quantitative data regarding basically content acquisition to acquire different movies. House prediction, we were able to find data that had both images and also had quantitative data about house prediction, and that was for both classification and regression. And of course, COVID diagnosis, that was actually a good example. So generally what we found is that the automated design using the selection hyperheuristic would then outperform the manual design, both in terms of the results that you obtain, but in addition to that, also in terms of the time it actually took to get the design. So we had reduced design costs. And in all these cases, the results produced were competitive with state of the art for those data sets that were manually designed. Okay, so the next study that I'm going to look at is something with neural architecture search. This was the case where we used a very simple hyperheuristic that produced very, very good results. So essentially with neural architecture search, you could look for the architecture that makes up the neural network, but in addition to that, you could also look for the parameters. So that was what was done in the study. We looked at both the parameters and we looked at the architecture as well. And what we did was we used a heuristic space, and I'll give you a diagram just now of how we changed what typically happens with neural architecture search. How many people have worked with neural architecture search? Okay. So what space do you typically work in? It's basically the architecture, right? You're working in the architecture space. So essentially, I think that's what people generally call the design space or the search space. It's also called the architecture space. So what we did is we created two new spaces. We created the the NAS operator space, and we created the heuristic space. So this came from trial and error. You could possibly work in the NOS space itself, but we found that if you worked in the heuristic space, this produced better results. So I'm going to introduce both the spaces to show how hyperheuristics can be used for neural architecture search. So we used a very, very, very simple hyperheuristic. It was a single point hyperheuristic. And when I introduced selection perturbative hyperheuristics, I spoke about selection perturbative hyperheuristics that have a heuristic selector and a move acceptance component. So we chose a very simple one that used a choice function. So basically what the choice function did is it kept track of the performance of the different heuristics. And it then, based on that, decided which ones to use. And the move acceptance was an adaptation of improving only. So the chess challenge, which was mentioned earlier, that was the move acceptance that was actually the winner for that chess challenge. Mustafa Mazir's acceptance improvement, the adaptive improvement limited target acceptance algorithm, IILTA. So basically what it does, it doesn't only accept if there's improving, it allows it to be a threshold difference between the best, last best value and what's, if it's not better, but that's within the threshold. But of course, that threshold is not static. That threshold changes as the hyperheuristic progresses. So a very, very simple hyperheuristic that was used to do this. But now comes the exciting part about the spaces. So as we spoke about previously, the standard space that's used is your neural architecture space. And you can have any architecture in there. You can have the whole architecture with the nodes. People have also looked at cell-based architectures now. So all the NAS benchmarks are based on the cell-based architectures where you have components and your optimization then chooses the components that you are combining together. So that's the typical space that you work in. The other space which we introduced, or the student introduced, was something called the NOS space. So the NOS space is the neural architecture operator space. So if you look at neural architectures, you can create them by performing certain actions. Like you can add a layer, remove a layer, swap layers, etc. So that's what the NAS operator space is. So you could actually just search the NAS operator space to find a combination of the operators that you want to use, and then use that to come up with a neural network, and you can do the optimization in that space. But what we did is we added a space on top of that. So we added a heuristic space that could then choose the operators, and then the operators would be used to create the neural network architecture. So if we look at that, you'd randomly create a NOS string. And then, and I'll show you an example now for NOS string. So NOS string could be add and layer, swap layers, etc. Once you have that initial string, what the hyperheuristic would then do is it will take that initial design, like you did with the initial design for everything else we looked at. It will take that initial design, and from that initial design, it will then apply heuristics or optimize heuristics to be applied to it to change that design. So that would go in, and then that would come back. That would then go and you'd go and look in your actual architecture space, and you will look at that architecture, and from that architecture, you will evaluate it. That gets sent all the way back, and the hyperheuristic will then do its optimization. So it was very, very cheap, and you'll see when I show you the results just now, it was cheap because of the type of hyperheuristic that we used. If you took something like a GA or we put something in there, so it actually worked better for the NAS benchmarks. It had lower times than the other techniques that were used for the NAS benchmarks. So in this approach, essentially what's happening, it's basically that operator string is where the optimization is being done in the heuristic, but you are right in the sense to evaluate that heuristic combination each time. Well, what we did is we didn't have a combination. We did one heuristic at a time because there was selection, single point selection. So we chose a heuristic. That heuristic then got applied to the NAS operator, but you're right, you are evaluating it over and over. You're evaluating your neural network over and over again. But if you look at using a GA, and if you looked at a GA and you had to evaluate the population over and over again, this is actually cheaper than that. Because if you had to use a neural architecture, if you had to use neural evolution, yeah. No, but what the other advantage was, and that is why we also tested on real world problems. The other advantage is if you're using the NAS benchmarks, you can do the queries in the benchmark to get it evaluated. So that's where I should also mention that because then you get a reduced cost because of that, because we used all the NAS 101, NAS 201, and NAS 301. Yeah. For the multimodal, yeah. So that it was parameterized beforehand. Yeah. So basically what we did is we based it on what was known to work for different problem sets. So we didn't train them ourselves. So we used pre-trained ones with the parameters and everything in. The idea is now with the work that the student's working on is she's optimizing the parameters. That has some limitations. Although it gave very good results, for scalability, it's not very good. So at the moment, all of that is happening now as part of the, yes, in that whole chromosome. So basically, we compared it to what was best known from the literature, but we haven't taken any other automated design techniques and brought them in and tested it. So for example, for this, we compared this to your standard GA that was used for it, and we compared it to all the techniques that were used for the NAS benchmark. So we took the techniques that were used, the best known for those data sets, and we evaluated according to that, according to time and according to performance. But it's a good idea to maybe look at other automated design techniques and compare. No, it's absolutely fine because they're very similar in certain ways. Sorry.
So I think one of the main criticism of the
Yeah.
is the interpretation.
Yeah.
But is it somehow the results?
So what you get out is basically a set of heuristics, a string of heuristics, and how that heuristic. So as a computer scientist, yes, you can read it. It has the same level of interpretability as a genetic algorithm does. So, genetic programming does. But genetic programming is meant to be interpretable, but we can interpret it. The humans can't interpret it. So there's still that gap of getting it out there for a layman to understand what's happening. And there probably needs to be some type of explainable AI. So the last topic, which I was going to cover, is explainable AI for hyperheuristics, but I don't think we're going to get to it in the session. Any other questions or comments before I go on? These are all very nice questions. Okay, so just to get back to what happens. So the question that we had from Tinkle is very important because he asked what happens with computational cost. That is one of the biggest challenges. So we wouldn't run things for very long. We'll stop our neural network early. But what helped with some of the data sets is if you're using NAS benchmarks, it has techniques built in it to actually reduce computational costs by just querying instead of reevaluating each time. But we did take this and apply it to 2 real-world problems, and the advantage of working with 2 real-world problems is we could see how scalable it was, and it actually did do well for real-world problems as well. So essentially what happens after that optimization, like I just mentioned, you'll get your best heuristic combination, which will then produce your best NAS operator, and from your best NAS operator, you will then get your best neural network in the space. Any further questions? So we've just changed the way that you actually do neural architecture search completely. We have played with working just at that level, taking out the heuristic level, but somehow the third level of indirection and third level of mapping by using a heuristic space does seem to give us better results. Okay, so what are the actual NAS operators that we used that would actually make up those strings in the NOS space? So it was very simple things: insert a layer, delete a layer, swap a layer, replace a layer, insert a connection, delete a connection, and then swap connections. Okay, and then the low-level heuristics that will then work in the hyperheuristic space, and the ones that we're finding a combination on to work on our NAS operator string, are things like replace an operator, swap operators, insert operators, insert in operators, remove an operator. The typical destroy and create, which is very powerful, no matter which area we work in, destroy and create works very, very well. And then a single point crossover within a NOS. So you're crossing over within a NOS, and then single parent cross over, uniform crossover, which swaps the middle within that NOS as well. Different crossover operations on your single string. Okay, so those were the types of heuristics used. Just to give an example again of how it all just falls together, that's where we create our string. So if you look at the SCLL-LCL, so that's for swapping a connection, inserting a layer, swapping a layer, inserting a connection, and we just randomly create that. That's how we started off. After we create that, we now have our first design, more or less to say, in terms of a NOS operator, and then we apply our hyperheuristic to that. And then we get the next one. And of course, we evaluate, and that's the part that you asked, how expensive that would be. And then that process is just going to continue. We send the performance matrix back to the hyperheuristic, and then we do this for I iterations. And that's essentially the overall. So if we look at what formed that hyperheuristic, and this is what helped us reduce cost, is by using a very, very simple hyperheuristic. Essentially, we had a heuristic selector, and it was a choice function, and it was combined with your adaptive iteration algorithm. But the choice function, essentially, a heuristic is based on how it works. We have rank values, and we also take performance into consideration, and like I mentioned before, pairwise performance. And then we had your adaptive limited threshold accepting algorithm, which I already just explained. It will accept things that don't improve within the threshold, and that threshold is dynamic. So what we did do in this work as well is, if we found after a number of iterations there was no improvement, we just recreated the whole NOS set of our NOS string again, and then we started again from scratch. So that was a NOS regeneration that was built in to move to another part of the search space if it did get stuck. So if we look at what we applied it to, we applied it to the standard benchmark. So NAS bench 101, NAS bench is the same as NAS 201, and then NAS bench 301. And the main reason we did this is we wanted to compare with other techniques that were used specifically for NAS. It also helped because we had a set of benchmarks to compare, but it also helped reduce computational cost. But then we also took a real world example. And I think subsequent to this, there's been some other real world examples that the student has applied it to soybean and also another data set. And this was paddy disease detection. And essentially, we found that we had reduced, I think we've done an analysis, and I've got the analysis. Basically, it seems that it gets to the right area of the search space quicker than if you search the whole architecture space directly by doing the indirect. And it's very similar to stuff that we found with combinatorial optimization, where you can actually get to the right part of the search space very, very quickly. Okay, and for the real world data set, the second real world data set that we've also applied it to, we took all the typical techniques, the standard neural networks that would be used for this, the state-of-the-art neural networks, and we ran with this. And in cases, we found that it basically outperformed it, but also there was some reduction in cost. Okay, so I think we only have about 20 minutes left, so I'm just going to give you the rest of the tutorial in a nutshell, but I'll take any questions before I go on.
Actually significant difference. So the involvement, like, so they get
So I do have them, and it actually it would differ. So in some cases, I don't think we ever found things that were exactly the same as you know, the state of the art. But of course, the performance was never exactly the same as the state of the art as well. But we also found that for different seeds, I think it dealt with a random number generated noise. Because for different seeds, you'd get a different architecture. We actually looked to see if there were any patterns through the architectures. Yeah, and that is why it was important not to just create one architecture. He actually did training and validation when he did the assessment of it, and then we had a different test set altogether for exactly the stochastic nature of it. Yeah, any other questions? So I'm just going to skip through this very, very quickly. So with machine learning and hyperheuristics, this area has started developing very, very quickly recently, mainly with the big boom of now using machine learning in optimization. So essentially, with selection hyperheuristics, there's been a lot of work done with reinforcement learning. Choice function is a type of reinforcement learning, but what is new? I mean, there's been some work done with random forest decision trees and neural networks. And generation, we've always used genetic programming as essential machine learning technique. But what is new is now using neural networks as hyperheuristics. So this is work that we did with Jorge and the group, where we actually used a neural network to create new meta-heuristics, and the neural network actually drove the hyperheuristic. So they were essentially LSTMs, but I'm not going to go through all of this in detail because we don't have time. But the main takeaway here was we could actually get meta-heuristics that performed better than the generic meta-heuristic. So basically, components were taken from PSO, genetic algorithms, and those building blocks, selection perturbative LSTM neural network was then used to actually create those meta-heuristics. Okay, so I'm just going to quickly go through it. If you do need these slides, I'm not going to spend a lot of time going through that. The other work that we worked on is the whole idea of a neural architecture search. And I think this is links to a question that came up earlier about doing things in real time versus doing things offline. So usually when you do a neural architecture search, you actually create your neural network. You do your architecture search and you use the static architecture throughout. The whole idea here was to actually make it dynamic, to change the architecture while the neural network was actually solving the problem. So that was dynamic versus static. And so essentially the design of your neural network changed in real time by taking into consideration information of what was actually happening in the weight space, the weight optimization space, while the neural network was running. And then the neural network architecture would change according to that. And it was both the architecture and parameters that changed. So what it would do is would learn from the first few iterations, and then it will then start changing its design based on what it learned. And again, a selection perturbative hyperheuristic was used to decide when to change the options and what options to change to. But I'm not going to go through all the details. I'm just going to quickly skip through this. And then what we essentially found, so it was a very simple choice function again with the ILTA that was used to decide which design options to actually make available to change the designs. In this initial study, we had a different design on each epoch, which is not cost effective, although it did run, you'll see we didn't have a big overhead in run times. We now use, as part of the optimization, the selection perturbative hyperheuristic also decides when to actually make that. And we've actually built in machine learning, a little bit of machine learning into that now. But I'm just going to skip through this and the details of it. These were the data sets that it was actually applied to. So it was a number of, again, image classification data sets. And basically, as you can see, we had three versions. We had static NAS, which is what we traditionally do. We had dynamic NAS, where we don't change the options available. And then we had DNAS, where we use the selection perturbative hyperheuristic to change the options that are available. And we can see that DNAS basically outperformed the other two techniques. If we go and look at the overhead, you can see there's a slight overhead, and in some cases there's a decrease as well. So there wasn't that big overhead, given the fact that it did more optimization than it should have, because you don't need a design on every epoch. You need a design on every n epochs. But still, there wasn't a very big change in the computational cost. And then this is just comparing to state of the art. So with the state of the art techniques, you can see in some cases it did just as well or even better than the state of the art techniques that were used for those data sets. Okay, any quick questions on this before I go on? Okay. So I'm just going to give this to you in a nutshell and then just go through the results. So essentially what we did here is we did function optimization. Now, a lot of the work done with continuous optimization, which also comes a lot from the group that was working in your university, is a lot of the early work that was done did not solve the continuous optimization problem directly. It would actually be used to design the meta-heuristic or the algorithm or the approach that was actually going to solve the continuous optimization problem rather than solving it directly. So again, there was work on coming up with meta-heuristics using hyperheuristics for continuous optimization. So what the student did in our group is he actually looked at solving the continuous optimization problems directly using a hyperheuristic, and he used a genetic algorithm hyperheuristic. So if you look at function approximation, basically you want to know the parameter values for the variables that form that function. And essentially that's what your chromosome was. Actually, that was what your initial candidate solution was. It was a randomly generated set of, I think I've got an example here. So I'm just going to quickly skip through this. So that is what your typical candidate solution was, but what the hyperheuristic did was work on that. So the hyperheuristic actually found low-level perturbatory heuristics to actually change that. So some of the things that if you look at that as an example, it would be remove a value, swap a value, increase a value, or decrease a value. So it actually changed the values in that, and the hyperheuristic actually found the right order and combination of the operators to change that candidate string. So those are the different perturbative heuristics we used, and that was just details about the genetic algorithm which you can find, which I'm not going to spend too much of time on. And then again, he had different benchmark sets that he used from the literature, so he could compare his work, one with 24 functions, one with 106 functions, and one with 24 functions. And then a different one, and we tried it for the different dimensions for function approximation, and it basically produced the best results for all across all data sets, for majority of the functions. Okay, so I'm just going to quickly go to this in a nutshell as well. We spoke about using hyperheuristics for automated design, but can we do automated design of hyperheuristics? And now what does it involve? As I said earlier, essentially when you're working with a hyperheuristic, you're doing exactly the same thing that you did with a meta-heuristic, but you're searching a different space. So all the automated design that we've done for any meta-heuristic, you can apply here. But there are some specific things to hyperheuristics that you cannot do generally for other techniques. And one is determining the set of low-level heuristics to use. And essentially what we do is we choose a set of low-level heuristics, and we use the same low-level heuristics throughout what we call the lifespan of the hyperheuristic. We're also creating hyperheuristics. Can you create hyperheuristics? How can you take the different components and create them? So there's work being done by two groups. One is Nessa Sabo from Nottingham, who did work on creating new generation perturbative hyperheuristics using existing components of existing hyperheuristics. And the other is by this group, Chung and al, who use a very, very simple Q-learning to actually combine components that make up your hyperheuristic. So they use heuristic selectors and move acceptance, and basically the Q-learning was used to actually create new combinations. They then ran it. So first of all, they'd use a heuristic selector to choose your pass that will actually make up an operator, a selector, and acceptance. And then they would use local search with the heuristic selected, and then the move acceptance after that local search will decide whether to actually accept that combination of hyperheuristics. So that's the one example, and it was placed 5th in the chess challenge. The next example, which was done by our group, was also used for the chess challenge. And the idea here was, instead of using the same set of low-level heuristics throughout the lifespan of a hyperheuristics, you actually change that set of low-level heuristics. And dominance criteria is used to change it based on the performance. So the whole set is not used throughout. It starts off with the set. You then remove things that are not working, and then you use some decision criteria to actually put it back in. So we call it dynamic subset selection. So usually you have the same set of heuristics that are used throughout the lifespan, but here we actually changed the set of heuristics. And we used we didn't use any optimization, but a simple dominance criteria to decide what to keep and what to change each time. So those are just examples of the information that's stored for each heuristic. And then we used different ratios of performance in the context of the heuristics individual performance, but performance compared to other heuristics as well to decide. And if you look at that, at this stage, when the student did this work, FSILS was the best chess winner, but you could see it actually performs FSILS in a number of cases and for different domains and across the domains as well. Okay, I'm going to go on for 5 more minutes. I'm just going to summarize the last two topics that I wanted to speak about, and then I'll just leave it open for any further questions. So the whole idea of transfer learning is you actually take knowledge from one algorithm and transfer it to another algorithm. Why would we want to do that? So there's two reasons. The one reason we can get better results, which is what we're aiming for, but also we can get a reduction in cost. Instead of learning things from scratch, I mean, this has worked in neural networks. So I think the whole idea of transfer learning, if you worked with transfer learning and neural networks, you'll know how powerful it was. But when it comes to evolutionary algorithms, it hasn't been used a lot. So there's a whole lot of work now done in evolutionary algorithms, but there's now also work done in hyperheuristics itself for transfer learning. I'm just going to give you an overview of the two main areas that we've worked in. So we've worked in it using it mainly in GP for generation construction hyperheuristics and basically transferring knowledge. And just to quickly go through, so the whole idea is you have some source data, that source data then gets transferred. So you'll have a source GP, you'll have a target GP, and you'll transfer knowledge between the both. And those are the main reasons that we wanted. The things that get transferred are elements of the population. You could have ideas from the things from the function set, terminal sets. We've done one with a generation construction hyperheuristic that is an ACO ant-based and colony-based algorithm. And basically the knowledge that was transferred, so we solved simpler problems that had to be solved, but we didn't lose that knowledge. Instead of having random pheromone maps, we've actually used pheromone maps that were transferred from the simpler problems to solve the more complex problems. And that's essentially, we did it for one-dimensional bin mapping, but that was known. But then we took a real-world problem for an industry we were working with, and also the quadratic assignment problems. Hyperheuristics weren't previously used in that a lot. And then we actually examined working with simpler problems as a source, the target problems with the more complex. It worked. It gave positive transfer in terms of both improvement of results as well as reduced cost for the movie scene in the quadratic, but not for the one-dimensional bin packing, which was interesting because it's clearly found that in some problems that are easier, because you'll notice your one dimension, if you look at you're looking at the number of bins, so it can flatline in a number of places. So for that, for simpler problems, it didn't work as well as it would work for something like the movie scene in the quadratic assignment. So we took simpler problems in each of those, and then based on that, we collected elements of the population. You'll see in the next work where we did GP for that. And for this one, we copied the pheromone maps across to the new ACO. And we resulted in improvements. So I'm just going to skip this because we did result improvements. What we found was with the one BP, because it was not as challenging as the other two problems, we did not get a positive transfer. So that's something to actually keep in mind. If we then look at the generation hyperheuristic that we use, it's basically transferring elements of the initial population of GP across, and that then formed the initial population for the more difficult problems. So we have to solve the easy problems anyway because we need solutions to them. So it's not like we're doing extra work, but we're actually collecting that information, and then we are now using it to solve the more difficult problems. Okay, and the challenge here was there's a decline in generalizability. Can you guess why there was a decline in generalizability? Because we assessed for optimality. It's the same problem I mentioned right at the beginning. When we were doing the actual optimization with the GP, it assessed for optimality and it didn't take generality into consideration. Okay, so I'm just going to stop there with this one. So the whole idea of explainable AI, and the main study I'm going to speak about is the study done by Ed's group. So this is a new field that still needs further development. And the main idea, and I'm just going to go through it in a nutshell, and Ed, please feel free to add at any point. The whole idea is, it was a question that you asked me about interpretability, because what can you actually see and what do you want to know? But I think from the work that we've been looking at and the work that I think you did as well, Ed, is we wanted to understand how the hyperheuristic is working so we can see how to improve the hyperheuristic. So the work that was done was actually looking at the different heuristics and looking at which point different heuristics, it was basically a visualization of which heuristics actually worked. And when I was doing this, I was thinking it would be fantastic to do this for our dynamic subset selection, is take the ideas for explainable AI and put it in there. It was the main idea to see which heuristics are used and how often they're used and at which points the most important heuristics come to play. So this is just giving an introduction of explainable AI, which I'm not going to spend a lot of time in now. The references are in the slides, but the main thing here, what XAI do we need in a hyperheuristic? So there's two types. There's types that we want to see as a researcher, but it's also linked to the way we want to speak to the non-expert and tell them what our hyperheuristic is doing. So the one is determining the effect of the heuristics, determining which heuristics are needed at which point, what parameters are effective, what's the most appropriate set of heuristics to use. And then, of course, when it comes to generational hyperheuristics, we want to actually see what's the right function set, what's the right terminal set, and work that we've just completed now is the whole idea of predicting when you can get stuck in a local optima. So from your source GP, you will actually train a machine learning technique to predict a local optima, and in the target GP, you will actually eliminate that. Okay, so if you are interested in everything I've discussed, our book is coming out in October this year. So there's details of everything I've discussed. Of course, this was just a little focus on some of the aspects. There's more in the book on the details of the topics that I've covered. And just to acknowledge the funding, all this work was done by two different funders. One is the broadcasting industry, which we work with, and the second is my chair funder, who's our NRF in South Africa. And there's a number of references. So everything I've spoken about, you can find in the references. Okay, so I'm going to stop there for now. We have 3 minutes for any questions or anything else that anybody wants to discuss. I'm not sure, Ed, if you want to add on anything to the explainable AI side or anything like that.
It's quite hard. It's quite hard to explain.
Yes, yeah.
Heuristics change their behavior during the process. Some heuristics start again. Got a little bit on transfer learning as well, I guess.
Do you need?
No.
Okay. Okay, any other questions or comments?
So one comment related to methodology is not to the
Yeah.
The quality objective.
Yeah.
Because you're taking the average, and so I think what would be maybe.
Yeah. So for that, are we looking for, these were just simple examples of how it can be done, but that whole idea needs to be evaluated, and we needed to evaluate with the proper multi-objective optimization experts. Yeah. Yeah. Okay. Okay.
Even if the distribution is number, I think it's better to
use. Okay. 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 Thank you. So we'll definitely include that. Thank you for your comment.
Yeah. So if I don't misunderstand something, most of the hyperheuristics you have are with some evolutionary approaches, no? Is there a particular reason not to have also included low-level heuristics like local search and so on, or yeah?
Okay, so they're not all with evolutionary algorithms. Most of them are your single point hyperheuristic with the choice function and IELTA, mainly because of the reduction in cost. So we had some, at one stage we did automated design of the deep neural network pipeline. And in the deep neural network pipeline, we ran a G8 hyperheuristic to do the design, and we ran the simple, but we actually started off with randomly selecting operators and accepting them if they improve only. And that actually gave us exactly the same results as the GA. So some of them have GAs, but the GA hasn't been too expensive. But most of our work is done. So you can, I mean, the random with improving only is a very simple one. And then, of course, as we got to more challenging problems, we needed more optimization in both the heuristic selector and the move acceptance component. And that's when we brought in the choice function together with IELTA. So most of our work is a simple single point selection perturbative heuristic with choice function and IELTA. I think there were 2 studies that we used the GA just because it wasn't very expensive. It didn't take that long as it did in other studies based on the nature of what it was searching for. Thanks. Okay, so I think it's 7 o'clock on the dot. If you do have any questions, please, by all means, I will be around for a few minutes after. And thank you very much for attending. I hope it met your expectations. And thank you for your help with that.
Nice to see you again. I'm in Germany. Yeah. Yes, I am.
Yes, now.
Yeah. Oh, it's going very well. Yeah, it's really good. Really good. Really good. But. Yeah, people were seeing that, but yeah, you yes, thank you for having me. Yeah. And I have to I heard it, but I didn't know what it was, so it's a good introduction. Thank you very much. I appreciate it. Good to see you again. Yeah. Okay. You can all over the world. Yeah. See you. Well,